So in this lecture we're going to look at a bunch of different questions that involve points, lines and planes and their intersections. So our first question says we'd like to find the point at which the line with parametric equations x, y and z intersect a particular plane. So the mental picture that we want to have is that we've got some plane given by this equation over here, and we have some line that intersects that plane given by this equation over here, and we want to find this particular point here where they intersect. So since we're given parametric equations, if we want to find a particular point on the line, we need to find the value of t at that point. And then once we substitute that t in, we'll get the x, y and z coordinates. If we want a point that lies on the particular line, then we're going to substitute that point into our equation for the line. So we're going to sub our parametric equations, which give us the equations for x, y and z in terms of t, into our equation for the line. Into the equation for the plane. So we've got 4 times 2 plus 3t plus 5 times minus 4t minus 2 times 5 plus t. Whoops, I've left out a plus here. 5 plus t, and we know that that needs to be equal to 18. And so if you work that out, you'll discover that the value of the parameter at that particular point is minus 2. So this gives us, if we go back to our parametric equations, we get x is equal to 2 minus 6, which is equal to minus 4, y is equal to 8, and z is equal to 3. So the point minus 4, 8, 3 is the intersection that we're looking for. Now, two planes are parallel if their normal vectors are parallel. So if ever you're asked if two planes are parallel, you just look at their normal vectors, which you can find from the scalar equation, and see if those two are parallel. And you remember that you can use the cross product to find if two things are parallel. If the cross product is 0, then they're parallel. You can also just see if one is the multiple of the other. On the other hand, if two planes are not parallel, then we know that they intersect in a straight line. So for example, these two planes here intersect along this line here, and we define the angle between them as the acute angle between their normal vectors. So you can imagine that this plane here might have a normal vector doing something like this, and this plane here has a normal vector doing something like that. And if we take the acute angle between them, so if we think about these two normal vectors, one like so and one like so, the acute angle between them is defined as the angle between the planes. So here it looks like a right angle, but it wouldn't necessarily be. So if we want to find the angle between planes P1 and P2, we also want to find the symmetric equations for the line of intersection, which we're going to call L, of these two planes. Okay, so we know that our angle between the two planes is the acute angle between their normal. Acute angle between their normal vectors. So first we need our normal vectors. Now normal vector 1 is going to be equal to, well, we look for the coefficients of our x, y and z term. So that's 1, 1, 1. our second normal vector is 1, minus 2, 3. So the next question is, how can we find the angle between them? Well, we can use the dot product, because we know that if we dot our first normal vector with our second, this is the same as n1's magnitude times n2's magnitude times the cosine of the angle between them. And it's this that we want. So we can rewrite this as cosine of the angle between them is the dot product of the two vectors over the product of their magnitudes. If we work out the dot product, we're looking at this vector dotted with this vector. So we've got 1 and then minus 2 plus 3. And our magnitudes, the magnitude of this vector, the first vector is going to be 1 squared plus 1 squared plus 1 squared, all square rooted, times by the square root of 1 squared plus minus 2 all squared plus 3 all squared. And if we tidy this all up, you'll find that you get the cosine of theta is 2 over root 42. So if you plug this into your calculator, and you be careful to keep your calculator in radians, then you'll get that the angle between them is 1.26 radians. So now we're ready to tackle the second part of this question, which asks us to find the symmetric equations for the line of intersection of the two planes. So just to remind ourselves, if we want to find the equation of a line, then we need two things. We need a point on the line, and we also need to have a vector in the direction of that line. And then we can put this into whichever particular form of the equation we want. In this case, we want symmetric. So now we need to find a point on our line L. So one thing that we could do is we could find the point where the line intersects the xy plane by setting z equals 0 in the equation of both planes. So let's have a look at what this gives us. So we're going to say, we're going to find So if we set z equals 0 in the first equation, we get x plus y is equal to 1. And in our second equation, if we set z equal to 0, we get x minus 2y is equal to 1. And the only solution that we have for this, if we solve these simultaneously, which is we're looking for the line that is the intersection of these two planes, so we are solving these simultaneously, will give us that x is equal to 1 and y is equal to 0. And we found this by setting z equal to 0, so this tells us that the point 1, 0, 0 lies on the plane. Okay, so we have found the first thing that we needed, which was a point on the line. So now we want to find a vector in the direction of the line. So we want to find a vector in the direction of the line. And here it's worth having a think about what our line looks like in terms of our two planes. So if we think about two planes that are intersecting and the line that is their intersection, we see that since our line actually lies in both planes, it must be perpendicular to both of the normal vectors, because we know that any vector that lies on the plane is perpendicular to the normal vector, and we know that this line lies on both planes, so it must be perpendicular to both normal vectors, which we've sketched here and here. So we can use that. So we know that L is perpendicular, I'm going to use a bit of shorthand here, to both normal vectors. But this is great because we know how to find vectors that are perpendicular to two other vectors. We take the cross product. So we can find a vector v if our vector v is given by the cross product of our two normal vectors for our planes. And if you work out the cross product, so we know that our normal vectors are the normal vectors 1, 1, 1. We're going to cross that with 1, minus 2, 3. And if you work that out, you'll find that that gives you the vector 5, minus 2, minus 3. So this bit has helped us work out part 2, which is to find a vector in the direction of the line. So the final thing that we need to do is we need to plug into our symmetric equations. So we've got plug into our symmetric equations, and we know that that's going to be x minus the x coordinate of a point on the line divided by the x component of the vector in direction of the line. And this is equal to y minus the y component over the y component of a vector in the direction of the line, and finally the same for z. And so there we have our symmetric equations for the line of intersection between the two planes that we've been working with. So now we've got a problem involving the distance between a point and a plane. So the picture that you want to have is we've got some plane, which is this over here, and we have some point that lies some distance away from it, and we'd like to figure out the distance, by which we mean the perpendicular distance between the plane and the point. So it's this distance d that we'd like to find. So let's do some thinking. What do we know? Well, we know about the normal vector of the plane. So we know that our normal vector points in the direction of p from the plane, and we know that its components are 1, minus 2, minus 2, which we've read from the equation over here. What else do we know? We know that if we have any other point on the plane, let's say p naught, and we draw a vector between p naught and the point we're trying to investigate, and we consider the triangle formed by the components of this vector, which I'm going to call b, which are perpendicular to the plane and parallel to the plane, then in fact what we've got is that d, which we're looking for, is the magnitude of the component of our normal vector in the direction of b. We want the magnitude of that. So we're basically turning this into a problem about vectors. And we know from the work that we did on vectors that this component of our normal vector in the direction of b is given by this equation here, where we're finding the amplitude. So if we think about this, what do we already know? Well, we already know the normal vector, but the question is, how do we find this vector b? Well, this vector b we find by finding any point on the plane and then constructing the vector from that point to the point that we're interested in. So what we need is, we need any p naught. So what can we do? Well, if you take values of x and y, then you can find the corresponding value of z on the plane. So for example, we could take x equals 0 and y is equal to 0, and that gives us that z is equal to minus a half. So we know that the point 0, 0 minus half lies on the plane. Or you could take x is equal to 1, y is equal to 1, and that would give you the point z is equal to minus 1 on the plane. So we've got 1, 1, minus 1. So I'm going to use this point on the plane for the first bit of the calculation, and then I'm going to do it again using this point so that you see that we actually get the same answer. Okay, so using 0, 0 minus a half, this gives us that our vector b, which is the vector from p naught to p, is going to be 2 minus 0, 8 minus 0, and 5 minus minus a half, which is going to give us vector 2, 8, and 5.5. And we know that our normal vector is 1 minus 2 minus 2, and so plugging into our equation for d gives us so we want the absolute value of our dot product, which is the absolute value of 2 minus 16 minus 11, and we've got to divide this over the magnitude of our normal vector. So that's the root of 1 plus 4. And if we pull that all together, we're going to get the absolute value of minus 25 over root 9, and so we finally get 25 over 3. So it might seem unlikely that if we used a completely different point p0 we'd get the same answer, which is why I thought it would be interesting to check if we use this point over here, do we get the same answer? So if we use that point, then for our b, which I'm going to call b1 just to make it clear that it's different, we get the point 176, or rather the vector 176. And if you do your calculation for d, you'll find that you want the absolute value of 1 minus 14 minus 12 over our magnitude of our normal vector, which hasn't changed, so that's just 3. And if you finish that up, you're still going to end up with 25 over 3. So that just shows it didn't really matter which of these 2 points. You could have used either of those or any other point. So if you want to summarize what we saw in this example to apply in general, we can conclude that the distance d from a point, and I'll just be clear here, we want the perpendicular distance from a point P1, given coordinates x1, y1, z1, to a particular plane, is given by the absolute value of a, which is the x coefficient of the plane times the x coordinate of the point plus corresponding b coefficients and points and z coefficients plus d. So this is an absolute value, because remember your distance, you want your distance to be positive, and you divide through by the length of the normal vector. So if you're good at memorizing formulae, this would be one to memorize. Otherwise, you can work it out using the logic that we used in the previous example.